This Zoom session is being brought to you by the Fractal Horizon Forming. Okay, today we finish off chapter 1, talking about inverse functions. Now, a couple of you have tried in section 1.1 as this whole separate section. Please don't. If I explicitly ask people to hand in all their chapter 1 sections at once, and it'll be a good fraction of the. It'll be a little whiles from now. Are any of you who still don't have the textbook? This is a question. Do any of you still need to get the textbook? I'm hearing no. All right. Well, okay. That means then let's just say then it will be your homework 1 should be handed in by the end of Thursday. That should be long enough, I hope. If you don't have the textbook, we'll discuss it with me after class, and maybe I'll let you hand it in a little later. Anyhow, we proceed. So, inverse functions. An inverse function is a function that undoes what an inverse does, what the function does. F of x is a function. Its inverse is written f minus 1 of x, pronounced f inverse. I'm not entirely happy about this notation because it looks way too much like a reciprocal, which it isn't necessarily. Anyhow, the idea is that f inverse of f of x is x, and f of f inverse of x is x. They undo each other. Whatever f sends x to, f inverse sends it right back again. So y equals f inverse of x if and only if f of y equals x. So for example, it's the opposite operation. For example, if f of x is add 7, x plus 7, then f inverse is the opposite of that, x minus 7. If g of x is twice x, the inverse is the halving function, x over 2. If h of x is the cube function, h of x equals x cubed, then h inverse is the cube root of x, the inverse function. The graph, here's a graph of y equals x plus 7. The graph of y equals x minus 7 looks like this. If this is the graph of y equals 2x, here's a graph of y equals x over 2. If this n-shaped curve here is a graph of x cubed, then it's this s-shaped curve here is a graph of the cube root of x. Now, for all of these, we have a kind of reflection going on. If this is the graph of y equals f of x, its inverse graph looks like the graph of f of x, only flipped, reflected through the diagonal line. The reason is simple. Y equals f inverse of x if and only if x equals f of y. That's the same as y equals f of x, only with the letters x and y flipped, exchanged. And that's equivalent to flipping through the diagonal because it turns the x-axis into the y-axis and vice versa. So that's how you get a graph of an inverse function. To find a formula for f inverse, we start by writing x equals f of y and then solve for y. So any inverse function is basic. It has a bit of algebra. It's basically an algebra problem. Solve for y in x equals f of y. For example, f of x equals 1 plus the cube root of 2x. Okay, this is a function that takes a number, doubles it, takes the cube root, then adds 1. Find the f inverse. Well, if y equals f inverse of x, then f of y equals x by definition of inverse. And then plugging in y into this formula, you get 1 plus the cube root of 2y. That equals x. Now we just solve for y. First, subtract 1 from both sides. Cube root of 2y equals x minus 1. Cube both sides. 2y equals the cube of x minus 1. Then take half of both sides. So y equals x minus 1, that cubed, that divided by 2. And that function, x minus 1 cubed, that divided by 2, is the inverse of f. Now note what happens with f of x with f inverse. With f, we take x, we double it, we cube root it, we add 1 to it. With f inverse, we take x, we subtract 1 from it, we cube it, and then we halve it. Each one of these are opposite operations in opposite order. That's what inverse functions are. Opposite operations in opposite order. Now, sometimes you get a problem with whether or not a function has an inverse, or at least has a single inverse. Take, for example, the graph y equals x squared. We flip it on its side, we get this sideways parabola, but that is not the graph of a function, because a single value of x will get you 2 values for y. In fact, if you the upper half of this graph is the graph y equals plus root x. The bottom half of the graph is y equals minus root x. So really this is not, these are two inverse functions for x squared. And they apply in different domain parts of x squared's domain. The problem being is that x squared sends two numbers to the same number. It'll send 2 to 4 and negative 2 to 4. And so if you try and invert that function, the poor function doesn't know which way to send 4 to, either plus 2 or to minus 2. So that means the problem here is that x squared is not what's called 1-to-1. It doesn't send, it sometimes sends two numbers to the same number. A function is 1-to-1 if different inputs always yield different outputs. A not B means f of A is not equal to f of B. So f has a single inverse, if and only if it's 1-to-1, if and only if it passes what's called the horizontal line test. That's sort of like the vertical line test for functions, only it's for horizontal. So you draw the graph, if every horizontal line meets it but once, then it passes and there will be an inverse. Here, however, we have a graph where horizontal line meets the graph twice, so it does not pass. This does not have a single inverse. So for example, is this function 1-to-1? Y equals 2.7 to the x? The answer is yes. Any vertical line meets it once. Its inverse, incidentally, will be called a logarithm. Is this function 1-to-1? Y equals 8 over x squared minus 4. Well, clearly not. This value, this horizontal line meets it twice. This one meets it twice. So it's, no, it's not 1-to-1. And if you wanted to invert it, you'd wind up with several functions. Maybe inverting this and inverting this. Excuse me, Philmore. Have you fallen out? Yeah, you fell out of the graph. Oh dear. Okay, invert here. Invert f of x equals 2x minus 1. Okay, so y equals f inverse, f of y equals x, 2y minus 1 equals x. Solve for y. Add 1 to both sides, 2y equals x plus 1. Take a half of both sides, y equals x plus 1 over 2. And that's the inverse function, x plus 1 over 2. Once again, we have opposite operations in opposite order. The f takes a number, doubles it, and subtract 1. F inverse takes a number, adds 1, and takes half. This one, well, okay, we can solve this. Invert f of x equals x plus 4 over x minus 3. Okay, so y equals f inverse means that f of y equals x, and then that means y plus 4 over y minus 3 equals x. So now we have to solve for y. Well, okay, the difficulty here is that there's two y occurs twice and there's a division sign. Okay, we'll get rid of the division sign by multiplying both sides by y minus 3. So y plus 4 equals x times y minus 3. Then you distribute the x. Y plus 4 equals xy minus 3x. We'll move the 4 to the right by subtracting it from both sides. We'll move the xy to the left by subtracting it from both sides. So after that algebraic maneuver, you get y minus xy equals negative 3x minus 4. Here we'll combine these two appearances of y into 1 by factoring it out. Y times 1 minus x equals negative 3x minus 4. Subtract both, divide both sides by 1 minus x. Y equals negative 3x minus 4 over 1 minus x, and that is the inverse function, negative 3x minus 4 over 1 minus x. Here they ask, invert the fifth root of x minus 7. Well, you get the same kind of deal, opposite operations in opposite order. So okay, f of y equals f inverse of x means f of y equals x. So the fifth root of y minus 7 equals x. Solve for y. We'll take fifth powers of both sides. Y minus 7 equals x to the fifth. Add 7 to both sides. Y equals x to the fifth plus 7. That's the inverse function. And again, opposite operations in opposite order. This takes x, subtracts 7, takes a fifth root. This takes x, takes a fifth power, and adds 7. And here we have another one. When we have a function in the form ax plus b over cx plus d, like this, it's called a fractional, I believe it's called a linear fractional function. It's related to something called 2x2 matrices. Yeah, so invert this. Okay, same before, y, f of y equals x. y plus 1 over y minus 3 equals x. And then we undo it by multiplying by y minus 3 at y plus 1 equals x times y minus 3. Distribute the x, y plus 1 equals x, y minus 3x. Move the xy to the left by subtracting it from both sides. Move the 1 to the right by subtracting it from both sides. So you get y minus xy equals negative 3x minus 1. These two terms have a common factor of y, so you remove it. Y times 1 minus x equals minus 3x minus 1. After division, you get y equals negative 3x minus 1 over 1 minus x, and that's the inverse function. Here we have a formula for converting between Fahrenheit, from Fahrenheit degrees to Celsius degrees. And so for various values of f, what's C, and find f in terms of C. In other words, invert this function. Okay, it's easy. Now if you plug in 59, see Celsius for 59 degrees Fahrenheit, it's 5 nines of 59 minus 32, which is 5 nines of 27, 15. So 59 Fahrenheit is 15 Celsius. See at negative 4, plug it in here. 5 nines of negative 4 minus 32 is 5 nines of negative 36. Churn, negative 20. So 4 degrees below 0 Fahrenheit is 20 degrees below 0 Celsius. Now, here we have the formula for Celsius. I'm going to solve for Fahrenheit. Okay, well, first we multiply both sides by 9/5. So 9/5 C equals F minus 32. Add 32 to both sides, then you get the Fahrenheit degrees equals 9/5 Celsius degrees plus 32. This is a Celsius to Fahrenheit formula. Here we have a graph of a function. Graph its inverse. Well, we flip to the diagonal and we get something like this. And there's the graph of the inverse. Okay, I think that concludes that part.